Hello and welcome to the lecture for the T-statistic for independent samples for Psychology 210. I am once again Dr. Chantel Marshall. Let me start this lecture with an overview of what we're going to cover today. We'll begin by discussing the experiment, how we set it up using a control group and an experimental group. I think that this setup for a study will probably seem very intuitive to most of you, since it makes sense to compare one group to another with only one thing that's different. And this will set up a specific kind of t-test that we need to run in order to see if any differences between those two groups are significant. So in order to have a control group and an experimental group, we'll be using a between subjects research design. So the way that we design our study always dictates the way that we analyze our data. And the between subjects research design always dictates that we're going to use something comparing our means. And for this lecture, we'll be using a t-statistic. Specifically, we'll be using an independent samples t-test to see if any differences we get between our two groups are significant. In order to calculate an independent samples t-statistic, we'll need to first find our estimated standard error. This should be no surprise given how you learned the single sample t-statistic. We always have to estimate our standard error because we don't have the standard deviation of our population. So instead, we'll use the standard deviation of our sample to estimate the standard error for our population. And then we'll do something slightly different for our variance. We'll be using what we call a pooled variance, and I'll walk you through how to calculate that. And then, of course, I'll show you how we conduct hypothesis testing using this specific t-test. Let's begin by going over how we conduct an experiment. As always, we begin with our independent variable. This is the variable that's manipulated by the experimenter. In other words, the experimenter decides what the levels of this variable are going to be and assigns them to participants. More importantly, this is the variable that we think is going to cause some sort of effect. And that's what we're interested in testing, whether it does actually cause an effect. That effect is our dependent variable. So after we've manipulated our independent variable, our participants go ahead and do something or react to something or fill out a survey or something like that. And then we test to see if our independent variable did in fact cause any differences in our dependent variable. For today's lecture, we're going to focus on a specific type of setting up an experiment. Specifically, when you manipulate the variable, you're going to end up with two groups. The first group is going to be your control group or control condition. Those mean the same thing. And this group doesn't get any treatment. It simply is your baseline group. So you might bring in this group and not do anything at all, and then see what happens with your dependent variable. You'll also have a second group, and this group receives treatment. And keep in mind that here the word treatment just means anything that we think is going to cause an effect. So it could be procrastinating or eating fruits and vegetables or sleeping more than 8 hours a night. It doesn't really matter as long as it's a difference between your control group and your experimental group. So in order to conduct a test to see if there's any difference between your control group and your experimental group, we're going to turn to the t-test for independent samples. And that's because these two samples, these two groups, are independent of one another. In many studies, they don't even know that the other group exists until the very end of the study. And so they don't have anything to do with one another. You're not trying to pair them up at all. They're simply two independent groups that you're going to compare at the end of your study. So let's go back to our tried and true research question. Do American men over the age of 35 get better sleep if they exercise regularly? I like to use this example because it shows how you can set up different studies to answer the same question using slightly different designs. So as always, our treatment here is regular exercise. However, you as the researcher want to define regular. In this case, I'm going to use 3 times a week as regular exercise. And our dependent variable is sleep quality. Okay, so we want to see if exercise changes the sleep quality of men over the age of 35. So in order to set up this independent samples test, we have to make and then compare 2 groups of men. The first group is the experimental group. So let's say that we recruit 25 men over the age of 35 and we give them an exercise regimen in which they exercise 3 times a week. And that's how we define regular exercise. The control group, let's say we get 27, they don't exercise at all. They just go about their daily lives the way they normally would. These particular guys like to video game, okay? So at the end of the study, we need to compare their sleep quality, those guys who are exercising pretty regularly, to their sleep quality, the ones who aren't exercising at all. So this test is going to allow you to do that. So when you think about this design of having 2 groups of men, one of which is your control that doesn't do anything different, and one of which is your experimental and they have something added to their lives, you want to think about them as representations, right? So our experimental group, the one that exercises, is standing in for the entire population of men over the age of 35 if they were to exercise regularly. So that is our sample. Remember, our sample should represent the entire population. We're not interested in these 25 men in particular. We're interested in all men over the age of 35 in the US. Unfortunately, we don't know their parameters. If we did, we probably wouldn't be collecting samples and making them exercise 3 times a week. But again, they're representing that unknown population. And we also have our control group to which we will compare our experimental group. And they are also representing a population. This is the population of men over the age of 35 if they did not exercise at all. And again, we don't know their population parameters. If we did, again, we could use a different test. So in this case, we're using 2 samples, sample A and sample B, to represent 2 unknown populations. A population of men if they exercised regularly, and that population of men if they didn't exercise regularly. And so we need to look at any differences between these 2 groups to see if in the larger population there would be a change in sleep quality just because of a change in exercise. So this is what we call an independent measures design. It uses a between subjects research design, which means that our participants are either in the control group or in the experimental group. So they don't go through both, they only go through one, and we will compare the 2 groups to each other. So these measures are independent of one another. Like I said, many of the participants in these types of studies don't even know that there was a separate group until the very end of the study. So we're going to use separate groups of participants for each treatment condition. And like we just went over in the last slide, these 2 groups represent 2 different theoretical populations. One if all men worked out regularly, and one if all men didn't work out regularly. So we're going to come up with a statement at the end of this study to say what happens if men exercise regularly. What happens to their sleep quality? So these are the 2 groups we'll be working with in our example. So let's quickly go over what our hypotheses would be. As you probably remember, the first step to hypothesis testing is laying out your null and your alternative hypotheses. And your null is really important because it's going to actually set up your t calculation. So let's look at our two samples. Remember, they're representing populations, so we're going to use mu in our hypotheses. So we now have two groups. Mu1 and mu2 represent the means for our populations for group 1 and group 2, our control and experimental, or experimental and control. The numbers are not as important in this case, but just remember to keep in mind which group is 1 and which group is 2. So our null hypothesis, as you might remember, is always that there's no difference, there's no change, zero, zippo, zilch, right? So in this case, what we're going to say is, even with different amounts of different amounts of exercise, we actually would not see a difference in sleep quality. That's our null, right? No differences, no changes. The way that we're going to represent that using statistical notation is that the difference, so mean 1 minus mean 2, between those two populations is 0, right? And of course, this is not what we want to be true, but we have to set up our hypothesis test as if it could be. So mu1 minus mu2 equals 0. So this means that the difference between our populations is actually nothing. And then, of course, we're going to test against that hypothesis. Of course, we have an alternative hypothesis for which we'd like to find some support. So the basic hypothesis is that there is a difference between our two populations, and that's saying that sleep quality between men who exercise and men who don't is significantly different. Right? So in this case, mu1 minus mu2 is not 0. It's significantly different from 0. Now, we're going to compare the difference between the sample means that we got to the difference between the population means if the null were true. So we're going to ask, is our difference between our two samples bigger than what we would expect if the null hypothesis were true? That's all we're testing for. Is this difference bigger than 0? But remember, we have to account for natural differences between our groups, right? They're not going to be perfectly the same in terms of their means. There's going to be small differences just because of normal, natural sampling error. And so we have to take that into account as well. So we have to take into account the estimated standard error, which you should now understand to mean sort of the average error you would get between any two groups. And we're going to take into account the estimated standard error for both groups. Remember, sample A is not going to represent the population of men who exercise perfectly. There's going to be some sampling error, right? So we have to take into account the estimated standard error for that mean that we get for sample A. And then we also have to take into account the estimated standard error for sample B. So now we have two errors that we're dealing with. Okay, so it's going to make our calculations a little bit messy, but I promise you it's going to be fine. Okay, so let's look at what T looks like for our independent measures. As you remember from the single sample T statistic, what we're looking for is a difference between the mean of our sample and the population mean if the null is true. And with the T, we have to estimate our standard error because we don't have the standard deviation of the population to calculate our standard error. Okay, so this is the normal everyday T statistic. We're going to add to it a little bit to take into account that we're not just looking at one sample's mean, we're actually looking at the difference between two sample means. Remember, we're looking at the difference between two groups, right? We're not just looking at one sample and how it compares to the population. We're looking at the difference between two samples and how they compare to the difference between two populations. So let's see what that looks like in a formula. So we're going to calculate the mean difference for our two samples. We're going to compare that to the mean differences of our populations, again, if the null were true. And hopefully you're remembering back to that last slide what it means if the null were true. And then, as always, we're going to divide it by our estimated standard error. What that tells us is the difference that we got between our two samples more than we would expect just from error alone, just from those normal natural differences we would get because we're working with a sample from our population. In this case, two samples from two populations. We're going to get some error in there, right? So is our difference bigger than that error that we would expect? That's what this formula is going to tell us. Now, in order to calculate these things, we're going to use this formula here. And these should seem very straightforward. The top should seem very straightforward. We're going to take our first mean, subtract our second mean. So these are the two groups that we've created. And then subtract what the difference would be if the null were true. And I just told you, what would the difference be if the null were true? So if the null were true, that means we have no difference at all, right? So this number here is actually 0, right? So we're going to compare our difference to no difference, right? So our difference to no difference. So this is 0. And then we have to use the estimated standard error of our combined two groups. And this is another formula, but I promise you it'll be fine. As long as you keep them straight and remember which one goes where, you'll be fine when it comes to calculating it on your own. So like I just said, I forgot I had that little thing in there to remind you. Like I just said, this is our null hypothesis, right? So our null hypothesis is that mu1 minus mu2 equals 0. Okay, so we now know the top part of our t. Now we need to figure out the bottom of our t. So for our sample, our estimated standard error measures the amount of error to expect between a sample mean and the population mean. Remember, we use standard error because we're dealing with a sampling distribution. Is our mean an extreme mean for our population? That's what we always are measuring with standard error. Except now we have two samples that we're dealing with, not just one. And so when we're dealing with two groups, we're measuring the amount of error to expect between sample mean differences and population mean differences. All right, so it's not just one sample compared to the population, it's the difference between two samples compared to the difference between two populations. All right, so we're going to calculate our estimated standard error in a little bit of a different way. We're going to use something called a pooled variance. All right, so when you think of pooling, like pooling your money together, right? It means bringing lots of things together into one pile. And so that's what we're going to do. We're going to bring all of our variance together from our two samples and put them together into one number. Okay, so each sample has its own variance. We're going to put them together. So pooled equals combined. So pool your resources. Think of those types of sayings. So now we're going to estimate the variance for both groups together. And I'm going to give you an analogy. It's sort of very similar to your weighted mean, right? So it's going to basically allow you to use the variance of two different sized groups. So I told you in the beginning, let's say that we had 27 men in our control group and 25 men in our experimental group. Those groups aren't even. And so the variance is going to be slightly closer to the larger group because they have more weight. Okay, so when we have different sized groups, then we use pooled variance. When you actually have perfectly similar groups, so if we had 25 men in both, the variance is actually exactly in the middle of the two groups. Okay, but when we use pooled variance, we're taking into account different sized groups. So like I said, this is similar to a weighted mean. Remember, with a weighted mean, we thought, oh, okay, well, there's more in this group than there are in that group. And so we have to take that into account because that first group is going to weigh more onto the mean. So just like that, one group may weigh more into that pooled variance. Okay, so let's take a look at the whole shebang together. So we're going to calculate estimated standard error, right? Usually this is what it looks like. So usually we do the estimated standard error to go on the bottom of our t-statistic. But again, when we're doing independent measures and those groups aren't the same, we have to use pooled variance. This is what pooled variance looks like. Okay, don't freak out. Take a deep breath. You can do it. I promise. So pooled variance is just our same tried and true variance, S squared, right? We've been using that for many weeks. And we're going to add a little P to it so that we know it's pooled. All right, so it's just our pooled variance is just that S squared we know to be our variance with a little P on it. So that is fine. And then what we're going to do to figure out our pooled variance is to use the sum of squares of both groups here. So we take the sum of squares of our first group and then the sum of squares of our second group, we add those. That's the top. And then we take the degrees of freedom from our first group and the degrees of freedom from our second group and add those, and those are the denominator. I want you to be very careful. Do not take your sum of squares for group 1 and divide it by your DF of 1, and then take your sum of squares of group 2 and divide it by your DF of 2. That is not the same number. That is not the same number. Okay? So make sure that you do it this way. Your sum of squares from group 1 plus your sum of squares from group 2, your degrees of freedom from group 1 plus your degrees of freedom from group 2. And then you take the top number and divide it by the bottom number. Okay, so that's how we're going to get to our pooled variance. But that's not even our estimated standard error yet. That's only this thing, right? Okay, so it's cool. We'll figure it out. All together now. All right. So, here it is. Take a deep breath. Let it out. Okay. I already showed you this, right? This is our first mean minus our second mean. And then this is our difference between our population means if the null were true. So that one is 0. Don't worry too much about it. The thing that's really going to take up a little bit of time, but it's not hard, is your estimated standard error. And that uses your pooled variance, which I just showed you, and then you use your pooled variance in this formula here, right? Where you use your pooled variance that you get, and then you take your group sizes, plug everything in, and then you take the square root of that whole thing. And then that's your estimated standard error. Okay, so I know some of you might be a little worried about all of these steps. I promise you, do it many times and you will be fine. Practice, practice, practice. Okay, so let's practice finding your estimated standard error because I think the top of your T for your independent samples is pretty straightforward. You're just working with two means that you get from your samples and then 0 to represent the difference if the null were true. It's that estimated standard error that's going to take a little bit of time, but I promise you it's fine. Okay, so let's assume that you have two samples, one of which has 6 people in it, and their sum of squares is 75. And you have a second sample, and it has 10 scores in it, and it has a sum of squares of 135. So we can see that our groups are not the same size, and their sum of squares is not the same. So we have to calculate out of this 2 things. First, our pooled variance, and then plug that pooled variance into the estimated standard error formula. 2 steps, shebang, shebang. And then you can go on and calculate your t. So the first thing you're going to do is find your pooled variance. Remember, this is like a weighted mean. You're simply looking to see what the variance is for both groups, but one group's going to pull it a little bit more towards them. Okay, so we use our tried and true formula. Those of you who have been working with me, you know I love to write my formulas down. I love it. I don't do it for my students. I do it for me, because otherwise I get really lost. So I would recommend that when you are working these out, write down everything, including your formulas, so that when you get to a number, you can be like, what am I supposed to do with this now? Oh, right, plug it into this other formula. Okay, so write down your pooled variance formula, right? We have our sum of squares and our degrees of freedom, which if you'll notice, right, we can easily plug in. So we have our sum of squares of 75 that we can put here. Our degrees of freedom for this group is simply n minus 1, so it's 5. We have our sum of squares for the second group right here. And then again, our degrees of freedom is n minus 1, so it's 9. Easy peasy, right? Okay, so again, we took our 75 sum of squares, our 135 from the second group. Our degrees of freedom for group 1 is 5 because it's simply 6 minus 1. And then our degrees of freedom for the second group is n minus 1, which is 9. Okay, so this is easy, right? Then we just do the math. So 75 plus 135, and then 5 plus 9. So we get 210 on the top. Let me double check. Yes, that's right. Okay, and then 14 on the bottom. That seems pretty straightforward. And then 210 divided by 14 is 15. Okay, that seemed pretty painless, right? So that's our pooled variance. Now we're going to find our estimated standard error. Okay, so our estimated standard error is this formula here. You'll notice that that number that we got for estimated standard error, 15, goes into this equation twice. We see it here and we see it here. Same number. Same number. And then we take our group sizes here, so it's no longer degrees of freedom, it's now our group sizes, okay? So we take 15, right? We just plug it in, right? And then we plug it in here. Sorry, I'm into sound effects right now. And then we take our group sizes, 6 and 10. So 6 here, 10 here. So easy, you guys. I know it looks complicated, but I promise you it's not. Okay, so then when you work it all out, you get the square root of 4. So 16 over 5 equals 2.5. 15 over 5 equals 1.5. You add those bad boys up, you get 4. Square root of 4, 2. So easy, right? So then you plug in that estimated standard error into your t calculation. And that's all you gotta do? That's all you gotta do. Okay, so let's look at what hypothesis testing looks like with your t for independent samples. No surprise here, it looks a lot like hypothesis testing with your single sample t. You're just calculating your t differently. Okay, so you always start with your hypotheses. Your null hypothesis, in this case, no difference between your two populations, right? The alternative hypothesis, there's a difference between your two populations. And you can even hypothesize a direction. So you can do an increase, right? So the difference is more than 0, or a decrease. Your difference is less than 0, right? So if we're doing one-tailed, which we'll get to, you can do that. So you set your criteria, which, as you should remember, your criteria are the parameters that you set in order to reject your null. Remember, our whole goal, reject that null, right? Okay, so are you going to conduct a one-tailed or two-tailed? Remember, a one-tailed test is if you have a directional hypothesis. I think that my experimental group will have better sleep quality than my control group. I would run a one-tailed test, okay, looking for an increase in sleep quality. And then you set your alpha. So this is, again, your proportion in the tails. So I'll go with a tried and true alpha of 0.05. So I have a one-tailed test with an alpha of 0.05. You should know at this point what your t is going to be. I'll let you figure that out and see if you're right. Then you find your t-value. You calculate the t for your data that you have. So the two mean samples and your estimated standard error that you have figured out, plug those in and then see what happens. Is it in the critical region, right? You cross your fingers, be like, please let it be in that critical region. Hopefully. And then you decide what to do with your null. Do you reject? Party time! Or do you fail to reject? I'm gonna go cry now. Right? Okay, so that is hypothesis testing. Should look very similar to what you've already done many times. All right, so I'm going to stop there, and we're going to move on to practice in the next video. But, get used to your formulas. Write them down somewhere so that when you go to practice, you can follow along. Okay, thanks everybody. Hope you enjoyed this video. Hope you're enjoying the T-Town party time. All right, bye everybody.